On behalf of 24HourAnswers.com, I welcome you to today's lesson. In this video, we're going to continue the real-world introduction to the derivative, and now we're going to see the equation of the tangent line unfold right in front of our face. In a previous tutorial where we first talked about a real-world introduction to the derivative, we found a bunch of average velocities, and these are really just the slopes of some lines. And as you can see here, we did all of these. Of course, I did fast forward through some of them as we realized how to find the slope relatively quickly, y2 minus y1 over x2 minus x1. And then ultimately we got down here to this, instead of it being an average velocity, we actually found what's called the instantaneous velocity. I emphasized to you in that video right at the end that this number right here is also the slope of the tangent line. And that's something that you'll find very often in calculus. You may find the equation of a tangent line. And that's what I want to talk about in this part. So we have the same scenario. A rock's getting dropped from a 100-foot cliff, same function, same pieces over here, the dots on our line. And this first question here is find the equation of the secant line through the point where the rock is at the top of the cliff to the point where the rock hits the ground. And this is going to be an algebra review. What I have here is that function graphed, and I have those same dots plotted on this thing. And what we want to find first of all, we want to find the equation of the secant line from the point where the rock is at the top of the cliff to this 2.5 comma 0, this green one down here. Sure, there are a bunch of dots up here, but I already have that line, and I'm going to remind you of how to do that. But this is the secant line. It passes through more than one point on our curve, and I'm going to show you how to get that negative 40x. And then we have several other secant lines that we're going to be building up to, and it's ultimately going to lead to what's called the equation of the tangent line at a particular point. Now, once you learn how to find a derivative the quick way, this will be really fast. For now, it's just going to be a lot of repetition to get you used to this and also really make you understand what the derivative truly is. So walking you through one example here where earlier in the previous video, we did find the slope over the entire time interval. That was from time 0 up to 2.5 seconds because we did solve an equation and figured out after 2.5 seconds the rock would hit the ground. This is the slope of that particular line. Taking that into account, we have m equals negative 40. And then we had 2 points. Our 2 points were 0, 100 and 2.5, 0. But if you watch that previous video, we kept talking about that 2.5, 0 because ultimately in the previous video, we were trying to figure out how fast that rock was moving at the instant it hit the ground. So I'm going to use this point and this slope with the point slope form, which is y minus y1 equals m times x minus x1. And I'm going to use this point with this slope. You could use this point, but I'm going to use this one because hopefully you'll see a shortcut with this particular point and a pattern where we can apply this to all of our equations of our secant lines and ultimately our tangent line as well. So y minus 0 equals m, the negative 40, times x minus 2.5. And hopefully you already see how this is going to help speed things up for us. Y minus 0 is just going to be y equals, distribute your negative 40, negative 40x plus 100. And that should have been a no-brainer there because if you really think about it, the 0, 100 was a y-intercept. But again, I'm using this point right here for a reason. Let's look at the second one. So notice the only thing that changed really is the point. Yeah, the 184 up here we had a 0, 100, but I'm still using that 2.50 because I'm finding the equation of the secant line that passes through the time intervals t equals 1 to t equals 2.5. Where recall from the previous video, t equals 1 to t equals 2.5, we did get a slope of negative 56. And all of these slopes here are going to be used as we find the equations of these secant lines. Now I'm going to go through these quick because they all work the same way. Y minus y1 equals m times x minus x1. So we do y minus 0 equals that slope of negative 56 times x minus x1. So I'm still using these two pieces here for my y1 and my x1 in my point slope form. And now we have another secant line. Repeating this for all of our other time intervals that we had in the previous video. Please go back and check that out to kind of get a refresher on how to find slope. And notice these slopes here from the previous video. Negative 72, negative 76, negative 78.4. All of these that ultimately led up to negative 80. What you'll notice is that all of these secant lines here use those slopes, and it's really just a matter of us doing y minus y1 equals m times x minus x1. Ultimately, we did realize a limit, so to speak, in the previous video, and this last question here is now find the equation of the tangent line. A secant line will pass through 2 points, in this particular case, for all these red equations. But then this last one down here, we saw a limit of our slopes. And as you can see, these slopes are getting close to negative 80. This is how fast that rock was moving right at the instant, right when it hit the ground. It was moving at negative 80 feet per second. From the previous video, we did discuss that the negative means the rock was simply falling down. That's indicating the direction. So this equation here is going to be what we call a tangent line. It's going to touch just that point, 2.5 comma 0 on the curve. Now let's go over to Desmos and look at this. So this orange one was that first secant line, that negative 40x plus 100. And then as I show some of these other lines here, I want you to notice that, okay, we had this one. This was the second one, question number 2. This is question number 3. This is question number 4. I hope as you see as I'm clicking on these slopes are starting to get more negative, right? And ultimately what we're doing is down here, these lines are passing through 2 points on the curve. But as we get closer and closer and closer, and you're going to start seeing these lines, they're almost going to become the same line. As I start clicking on these until right there, this purple line that you can barely see, and I'm getting ready to hide all the other ones, all of these other multicolored lines are technically passing through 2 points on the curve, whereas this one is tangent right at the point 2.5 comma 0. And what I have done now is I've gone back and I've hidden all those other points, all those other secant lines, and if I were to zoom in, you see this purple line here, this is our tangent line, that last equation that we found back over when we were writing the notes down, negative 80x plus 200. This is the equation of our tangent line. And if I zoom in, you're going to notice that there is a little gap between the red and the purple, both here and here. Technically, this is the only point where this purple line touches that red curve, and that hence the tangent line. It skims right across it. It does not pass through 2 points here. So this is our tangent slope, our derivative when time equals 2.5. This is the equation of our tangent line at the point 2.5 comma 0. Again, you will be doing this a lot throughout differentiation in Calculus 1. Find the equation of a tangent line. Find the equation of a tangent line. And ultimately, you're going to be able to find these derivatives very fast. And finding the equation of a tangent line is, once you know the derivative, that is your slope, it's actually your tangent slope, and then you can simply do point slope form, y minus y1 equals m times x minus x1 to find the equation of your tangent line. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.